And what is CDF? Now let's look at the CDF. CDF is circuit description format, and it's used as a central database, and it is continuously updated throughout the characterization flow. As and when the characterization is proceeding, simulation happening, vectors are getting generated, functionality is being verified, and all of that happens with the help of config and CDF. So if you don't like something, you can intervene, change something, and rerun your flow, and it'll take it from there without changing what you changed. So user always has a precedence. It consists of information used and derived by Guna's BEST engine. So BEST engine is essentially an acronym for 4 engines Guna has internally, which it uses for characterization and other features. The B stands for Boolean, whereby looking at a circuit, it can identify what kind of circuit it is. E is for electrical. It can also extract some of the electrical characteristics, like looking at the cell or the circuit. And then it also has a stimulus generator, or along with the search engine. Stimulus is where it generates the vectors for different model types like delay, power, noise, and so on and so forth. And temporal is used for finding out timing arcs. It is essentially helpful in the noise, CCS noise, as we would see later on. So these 4 engines are at the heart of characterization engine, which we call BEST engines. And other than that, we have machine learning engine, which also helps in actively in identifying what has been done and what's coming. And it also has search, whereby it can search for patterns inside the large circuit. BEST engines do following things. It identifies, recognizes the circuit functionality, generates the stimulus, it fires simulation, and identifies some of the electrical characteristics of the cell. And it has model arc, simulation result, and rest of the miscellaneous information. So all of that is part of your CDF. And we will open the CDF and I'll show you how that looks. Actually, function CDF is I've already shown you that the function is similar to what Liberty has. It's very simple. It's kept like that for a purpose. CDF has some of these additional functionality types. So combinational, you already saw. Any Boolean equation is what it is. Your combinational function. It also supports tri-state, latches, flop, and state tables, and those all are part of Liberty, and they are kept as is for the ease of use. Because you already know Liberty, it should be easy for you to modify, change, or add a new CDF function. So CDF function is used to understand the functionality of the cell, and CDF function along with other properties is used to derive stimulus for various characterization types. CDF vectors. We have not seen that yet. I'm going to show you in the next lab what those vectors are, but those vectors essentially help drive the simulation. They are in the form of 0 and 1s for inputs, and rise and fall and some tri-state transitions for outputs. An example of that is shown on the slide. And like you see, you have a bunch of 0s and 1s separated by commas, and then equal sign, and then you have rise and fall. So that's essentially your one vector. Which is used for the model generation. Which model? We will cover that in the next slide. And you would see that those being generated automatically. Either you can generate them from the netlist, you can generate them from the pattern matching, you can generate them from the CDF function. So there are multiple ways to generate these stimulus. And most of that is automatic. You don't have to worry about it. But if you don't like what it has generated, for example, specifically for large IPs, where it did not understand it perfectly, you can go ahead and modify some of the things that you did not like, and that's perfectly okay. So what are these vectors? So I'm going to take a very simple example of a D flip-flop, DN clock, with 2 outputs, Q and QN. And in the highlighted portion, you see the delay vector. Essentially, it's giving, so the first one is D and the second one is CLK. So D is 1, CLK is 0, and it changes. D stays at 1, clock changes to 1, and then D and clock goes to 0. Both of them are changing, and D stays at 0, clock goes to 1. So this is your delay vector, and you're saying output would be rising. So essentially it is shown in the picture on the right hand side. This is what it sees. If you see 1 0, which is at the end, the beginning of your simulation, so that's your 1 0. The point starts at t is equal to 0, and the cycle time determines when it changes next. So you're saying 1 0 to 1 1. The second state is 1 1 here. So this is your 1 1. If you want to track the input and output, essentially we are tracking green and blue lines. And green is staying here at 1 until it changes. D is red and CK is blue. So red and blue. Okay, so D is your red. Actually, that doesn't look right. Let me see again. So D is 1 1 0 0. 1 1 0 1. Okay. So this picture likely does not match with this vector, or I don't understand. So I'm going to move on. I'm going to ignore this picture for now. And essentially what I'm trying to explain here is these are D and clock vectors that is causing the change in the output. So 1 0, 1 1, 0 0, and 0 1 will change the flop state to rise and fall, and that's your delay vectors. And the last two vectors, last two states, input states 0 0 and 0 1, which is input D and clock, tells you what is switching and what is not switching. So essentially D is 0 and clock is rising. So only clock is changing, which is clock rising, and output is rising and falling. So output rising and Q rising and QN falling. And you have this model. So with this information, you can generate the model. Looking at the last two vectors and the output, the models are model delay clock R QR and model delay clock R and QNF. And that's your model, which will eventually we simulated, collected results on, and the same thing will show up in your Liberty files eventually at the end of characterization. So this is your CDF syntax detail. Very small, but very powerful. And you will see that it can be really, really huge for even simple cells like, DFF and stuff. It goes to several hundred lines. But this is the syntax of CDF. And if you end up writing a CDF, this is what you would end up using. And this is one simple example. It's inverter. It's not even complete for inverter. It's what it looks like at the end of your characterization. And it uses this CDF, the data in the CDF to generate the Liberty files. So again, you can use that information to change the Liberty file if you find something missing, or you can add something by hand and it'll show up in the Liberty file. So now with that, we have a couple of commands that are very useful to check the syntax. Essentially anything that starts with read is your read command. So we have read CFG and read CDF, which takes these two files, CFG and CDF files, and it runs in a fraction of a second. And if you end up editing that file, use these two commands, and it'll tell you if there is something wrong or not. And you can do the same thing for the spice. Most people don't write spice by hand. So if something is wrong, you can check it before you start the characterization.
So Rohit, just a minute. I was just checking with Pravashi. So Pravashi, does that answer your questions on CDF, or do you have anything else?
Yes.
Anyone else has any questions on CDFs? You can bring up it on the chat box, or you can ask it directly. So if not, we'll move forward. Yeah, Rohit, we'll move forward.
Okay.